Okay, we're reviewing bonding with this activity, and you should have gotten it throughout the week when we covered it. However, let's go ahead and do some sample problems here, and then move on to each of the other parts of the work you had on Friday. As you move through this activity, make sure you've tried each of the sheets. I'm going to give you probably 30 seconds before I display all the answers rather than walking you through the answers. I think this is a way to shorten the video time. But I'll do a couple example problems and try to do the more difficult ones as we move along. Okay, so ionic bonds seem to be pretty straightforward from what I've seen in class. You guys have seemed to have gotten it. And what you look at when you look at an ionic bond is you draw out the valence shell of each of the reactants. Remember, the reactants are on the left side of the equation. The products are on the right side. So we start with one lithium and one chlorine, as you can see here. Lithium's valence shell electrons is a 1, right? And chlorine has 7. And so when chlorine was more electronegative, comes along and meets up with lithium. And before I go any further, let me say that when you're talking about ionic bonds, it's much easier to identify them than having to go ahead and calculate electronegativities. All you have to do is look at the periodic table and see that chlorine is on the far right and lithium is on the far left. In fact, lithium is in group 1, right? And chlorine's in group 7 or 17, depending on what the numbering system is. But it's on the far right and the far left. You can be assured that it's going to be an ionic bond. Now, when the chlorine comes in and takes that electron, as you see it's happened here, chlorine gets a negative charge and lithium a positive charge. And based on our two rules of bonding, we know that these two are going to stick together in order to minimize their charge. So the negative and the positive together equals 0. 1 plus 1 minus 1 equals 0, right? So we have a neutral group, ionically bonded pair of atoms. Each has a full octet. Now you might ask, well, how does lithium have a full octet if it only has 2? This again goes back to the rule that we stated repeatedly throughout the week. The first shell only holds 2 electrons. Lithium only has 2 shells, one little lone electron in the outer shell. By getting rid of that 1 electron, its inner shell is full, even though it only has 2. Chlorine has 7 in its second shell. Rather than getting rid of 7, which would be difficult, energetically speaking, it takes up that extra electron and has a full octet. Both atoms end up being neutral as long as they stick together. You can do calcium oxide on your own. It's almost exactly the same as lithium and chloride, except the calcium is in group 2, which means it has 2 electrons in the outer shell. And remember, oxygen is in group 6 and needs 2 electrons. Calcium has 2 extra ones. Oxygen needs 2 electrons. And so you can envision the same process happening, except this time with 2 electrons. I'm going to let you draw it out. You can draw. I would fill this in first before I start drawing, so you know what atoms you're dealing with. So in the case of lithium and chloride, it would be lithium and chloride, or lithium and chlorine. And the valence electrons for lithium is 1, and the valence electrons for chlorine is 7. Again, you know that by the shortcut I taught you on the periodic table. Electron transfers from each. Lithium's going to lose 1. And chlorine's going to gain 1. Ions formed in the product, you form lithium plus and Cl minus. And you can do the same down here. In fact, I'll fill it in for you. You go ahead and do the drawing. And that's a calcium and oxygen. And the valence electrons for calcium are 2. So there's 2 here, and this has 6 valence electrons. And this is going to lose 2. Let me fix that. Lose 2. And this is going to gain 2. Now here we're filling in the second shell, so you want to fill in 8. And so 6 plus 2 is 8. And the ion you form here is a calcium plus 2, and an oxygen -2. All right. Now why is that? Because I need you to remember what's going on at the atomic level. At the nuclear level, oxygen is element 8 and therefore has 8 protons. If you're adding, it has 6 in its outer shell, but 8 protons altogether and 8 electrons altogether. Now remember, 6 electrons in its outer shell doesn't mean it's 6 total. There's 2 electrons in the first shell. So 8 protons and 8 electrons, it's electrically neutral. But now when it gains those 2 electrons in calcium to fill its octet, it gains 2 more electrons. So it makes it a -2 charge. All right, so let's go ahead and do this beryllium. Now, they did not balance the equation in the form. You'll notice that beryllium and fluorine are added together and they make beryllium fluoride. Notice that there's 2 fluorines here. So I went ahead and added a 2 in front of the symbol for fluorine on the reactant side. So you need 2 of these and you need 2 of these at the end. So if you have 2 in the end, you had to have 2 to begin with. As you can see, fluorine has, and we'll go ahead and put it in the chart. Fluorine is in group 7 and has 7 in its outer shell, and I should say fluorine. I'll keep it the same and put the metal on top and the non-metal on the bottom. So beryllium being the metals on top and fluorine being the non-metals at the bottom. Valence shell electrons for beryllium are 2 valence shell electrons because it's in group 2, and valence shell electrons for fluorine is 7 because it's in group 7. So when you transfer the electrons, you know you're going to transfer from beryllium 2 electrons, and each atom, and you'll notice that here's from and to each atom, right, is only one electron. Now the question that you have to think about is how is it that this electron, how is it we're only transferring 1 electron if we have 2 electrons for beryllium? We need 2 atoms, right, of fluorine. If you're only dealing with fluorine, if fluorine's your only option, then you need 2 of these fluorine atoms to take up your 2 electrons, because each fluorine atom is only going to be able to take 1 to fill its octet. And what are the ions you're making? You're making beryllium ion, right? And you're making fluoride. Usually when you add a charge to it and the non-metal gets an IDE at the end, you don't have to remember that, but just so you know. But you have 2 of these, right? So you have 2 of them. So it's a -1, but you have 2. Now you can go ahead and do the same with magnesium, and magnesium is another one of those +2s, and sulfur is one of those that needs 2, right? So magnesium wants to get rid of 2, and sulfur takes 2. Pretty much a similar problem that you have with calcium and oxygen. In fact, if you'll note, the calcium and magnesium are in the same group, and so are oxygen and sulfur. The trick is that magnesium is in the 3rd shell, and calcium is in the 4th shell. If I were you guys, when you're doing the drawings, and this is just a suggestion, you can go ahead and draw the full board diagram if you want. I would just stick to the Lewis dot structures. So just all you really need to worry about is the outer shell. But if you do that, remember that when you get rid of that outer shell and you're drawing it over here, you have to draw in those inner shell electrons at that point. So in other words, let me go ahead and do let me do an example with potassium and fluorine. Potassium is in the fourth shell, right? And it has 19 electrons, but I'm just going to put in the valence shell. And the valence shell is 1, so I can put in potassium with 1 electron in its outer shell. Then I go ahead and I do fluorine, and I know that fluorine, again, not drawing the inner electrons, has 1 electron in the outer shell. When I bind it, I'm sorry, not 1, that's my bad. 2, 3, 4, 5, 6 has 7 electrons, and it wants to get that 8th one. It wants to take this electron from potassium and bring it over. When it does so, potassium now has a full outer shell. Potassium has 8 in its outer shell. 1, 2, 3, 4, 5, 6, 7, 8. It had to have 8 because they wouldn't have been able to fill it. These electrons only go in shell by shell. So you can't fill in the other one until the inner shell is filled. There's an exception to that, and that's the D block elements. That's why we try not to deal with them. Those are those transition metals, those coppers and cobalts and chromiums. They behave a little oddly, and there's actually a really good reason for it. But again, this is not the class to discuss it. All right, so if we look at this, there's potassium with a filled octet and fluorine with a filled octet, each having 8 electrons. 5, 6, 7, 8. 3, 6, 7, 8. So each has 8. Fluorine has now a -1, and potassium has a +1. And they stay near each other, and they become neutral because 1 minus 1 is 0. So these atoms, they behave. You can draw these with or without the inner shells. Drawing potassium with the outer shell, not the inner ones, gets a little. Somebody asked me a question about why is it, if there's 18 electrons, that how is it possible that, and then we're only dealing with an inner, they only have 2 or 1 in the outer shell. If you did the Bohr atom, and I'm only doing this because someone asked me about it, but if you did the atom of potassium and you looked at the inside, so this is potassium, then the first 2 electrons are fill in the 1s. Then the second shell starts to get filled in. Remember, the first shell 1 only has an s, but the second shell and beyond has an s and a p. So there's 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8. Now that shell is filled. And the question is, if potassium is 19, that's what potassium is, right? 19 protons. How many electrons will it bring in? It will bring in 19 to become chemically neutral or electrically neutral. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8. But only 8 can fill in. 8 fills in this shell. So if you're going to bring in more, you have to move on to the next shell. So 2 is in the first shell, 8 in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. The next you fill in is the third shell. Now, potassium is not in the third shell, is it? It's in the fourth shell, fourth energy level, fourth row of the periodic table. So that also makes sense if you think about it. You have 19 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 shown. So you're going to draw another 8 here because each shell can has a maximum of 8. 4, 5, 6, 7, and 8. So there's your 8. They would be normally evenly distributed. I didn't draw it that way. And of course, so now they have 8 and 8, 16, 17, 18. You have 1 more electron. Well, if you notice, potassium, like all its brethren in that first column, has only 1 little electron in its outer shell, even though it has 19 protons and 19 electrons. it still only has one in its outer shell. Just like lithium, just like all the others in that particular column, sodium, rubidium, cesium, francium, they all have one electron in the outer shell. The inner electrons, or all the inner shells, are filled. So as soon as potassium gets rid of that electron, and I'm just drawing the outer shell now, you're going to have your 8, 2, 3, 4, 5, 6, 7, 8. You have your 8 electrons, and it has a positive charge. So it has a positive charge because it's missing that electron that you have here in the outer shell, and you have a full outer shell. So these atoms, these chemical reactions on this page will do exactly as the ones that we saw on the previous page. And all you got to do is find the valence electrons for each of these atoms, and you can find them on the periodic table in their particular groups. So aluminum is in group 3, right? So it's going to have 3 electrons, and chlorine's in group 7, so it has 7 electrons. And then you see that you need 3 of these chlorines to take on those 3 aluminums that are 3 electrons that aluminum is going to lose. Of course, if you want to balance the equation, you really should go ahead and put a 2 in front of this chlorine, or actually 3, right? So there's 3 chlorines on the right. There should be 3 chlorines on the left. So in any case, it's important you go ahead and balance the equation. Remember that's going to be on the exam as well. Why is it important to balance the chemical equation? I'm not going to require you to balance the chemical equation, but I will have you recognize whether the chemical equation is balanced or not, and I'm going to have you answer questions that have to do with why is it important to do so. Okay, so if you have aluminum, then I'm just going to do just the Lewis dot with 3 electrons in the outer shell, right? And you're combining it with 3 chlorine atoms, each one of them having 7 electrons. What is going to happen, and I hope everybody can answer that already, hopefully you've already done it, is that each one of these electrons is going to get taken by its own chlorine atom. And so what you'll end up with is 3 chlorine atoms with a full valence shell. Each atom of chlorine having a -1 charge, and aluminum having a +3. And if you had to fill in the chart, again, you'd say it was aluminum and chlorine, and you would, let me change the color of that. Aluminum and chlorine, and the valence electrons for aluminum are 3, chlorine 7. Electrons transferred to 3 for each chlorine atom. It would be 1. The ions formed in the product are Al +3, and the chlorine is Cl -1. And you can go ahead and do that with all of these. Now, the trick is when you come down here and you see lithium needs 1, it only has 1, and nitrogen has 5, needs 3. How many lithiums do you need to fill that in? I hope you say 3 lithiums. You're going to need 3 lithiums because each lithium only has 1 electron. I hope you understand that. And that's kind of a bit of a trick question for you, where nitrogen has 5. It needs 3. So you'll see the transfer of electrons go here, here, and here. So that way the lithium has its 2 in the outer shell, and the nitrogen has its 8. And if we take again we do a lithium has 1 valence electron in its outer shell. Nitrogen has 5. There's going to be 1 transferred for each lithium. There's going to be 3 transferred to it, and the ions formed a lithium +1 and nitrogen -3, right? That's the ion that's being formed here. And you'd go ahead and do that with all these atoms, all these different species, making sure that you know how many atoms you're going to need to fill in these electrons. Here you have again, the elements of the periodic table, each of the groups, 1, 2, 3, 4, 5, 6, 7, and what charge you get. How many electrons do you need? Do you need to either get rid of if they're positive or take if they're negative, right? All right, so sodium, give a loose dot structure for each of the following atoms and ions. So for sodium, it's going to be Na. For sodium ion, it's Na. That's with Na with a full octet, right? Na plus with a full octet. Why am I putting 8 if it's sodium? Because now it's the ion, right? And that's going to be a +1 charge, which in a sodium, regular sodium only has 1. And so what you see here is that sodium without a charge has 1 electron in its outer shell. Sodium with a full octet has a +1 because it lost that. And you do the same with each of these. I think you can handle that. And then it says, draw the electron dot formulas representing each of the following. Sodium atom, chlorine atom, react with each other to form sodium chloride. You've done that over the last a couple pages, so you should be able to do it. Do the sodium atom here, do the chlorine atom here, however many electrons it is. I could tell you, but I'm sure you know, and you've done it in previous pages, and in fact, I think I did chlorine for you a little earlier in the video. So chlorine atom react to form sodium chloride, and these are two sodium ion and chlorine ion together. They stick together. Same thing with magnesium and oxygen atom to form magnesium oxide. Aluminum reacts with nitrogen to form aluminum nitrate or nitride, right? You guys can do it. In fact, I think I've done some of these, but don't go back and look at the video. Try to do it on your own. Now here's some information on atomic radius. You really don't need to know it for the exam, but it's kind of interesting background information to let you know what happens to these atoms as they come down, as they coalesce, as they give up electrons or take electrons on. It turns out that the atoms, actually the sodium atom, for instance, gets smaller as it loses its electron. That makes sense. It lost a whole shell. And then the chlorine atom actually gets a little bigger. And what you see here is you see the array that it forms. And why is it the sodium chloride is, if you look at it in your palm, is a cube? It is such because the atoms line up in such a way as the positives and negatives attract, and the negatives that repel each other are as far away as they can be and still be attracted to the positive charges. So it's a kind of three-dimensional representation of the sodium and chlorine ions combining with one another. I wouldn't really worry so much about the atomic radius, although it does impact a lot of things in biology. It's important right now, not that so much that you understand the atomic radius impact, but it's much more important that you understand that the positive and negative ions attract one another in a solid form. And later you'll find out that they go into solution because water is polar and it gets in between these bonds. Now when we take a look at ionic compounds, you should always also note that ionic compounds as solids have a very high melting point. So if we would put you, if you go and cremate a human being that's passed away, their body is turned mostly into carbon dioxide, and what's left is a bunch of salts that have not even melted inside that furnace, and that's because it takes a very high temperature to melt that salt that's in your body. So salt melts at very high temperatures. Remember, melting is not the same as being dissolved into water. Melting is having a liquid form of the salt. All right, so all that being said, this is not a big piece of the test. This is just a background sheet. So if you don't understand it, I wouldn't even worry about it. But it's interesting what happens if you do understand it. You are interested. It's an interesting page. Now again, we're going to go ahead and previously we were working with some Bohr atoms, and I told you you're going to go ahead and switch to the Lewis dot. We already covered this in class as well. And if you take a look at the electron dots and you look at hydrogen, the hydrogen atom is just simply a hydrogen with just one electron in its outer shell. And you add it to another hydrogen atom, and it has another electron in the outer shell. And then together they're going to form kind of this, right? Or H2 gas. And we've worked with hydrogen gas in class, and this is just another way of saying hydrogen gas, just two hydrogens. We assume that everybody understands that hydrogen can only make one bond, so it's a single bonded atom. And if we wanted to draw it so that it made a little more sense kind of in its atomic structure, we draw it more with these circles the way you see here in this diagram. And if you drew it that way, you'd see that at each connector point here is two electrons that the two atoms share. And they share it evenly because they're the same atom, and so therefore it's a nonpolar bond. But you'll notice that each molecule is covalently bonded here, but not all of them are nonpolar. Some of these are very polar, like as water is, ammonia. Methane is very nonpolar. Actually, ammonia is nonpolar as well. So these two are nonpolar, while these two are very polar. So it's interesting that even though they're covalently bonded, even though they're sharing electrons, these are sharing. This one's definitely sharing it evenly, where this one's not. And so what determines what elements are share evenly and which don't? Now this is very important for biology. So it's probably the only reason we even discuss a lot of this bonding stuff is so that you understand this point, that nonpolar, the difference between nonpolar and polar molecules. Now here's again some more drawings of what happens to valence shell electrons. Why this is a written description as to why atoms form these bonds to be more like noble gases, to have 8 electrons in their outer shell. In the case of hydrogen 2, these are electron density clouds. Remember we talked about the idea that if we were going to be more honest, a better model for demonstrating how atoms share electrons is this cloud concept. But it's not as useful for us for our discussions, so we tend not to use them in a classroom. But it's nice to draw them out and remember that what we're talking about is that the electrons spend more time around fluorine because it's more electronegative, but hydrogen's still there, and it does spend some time around hydrogen. So this is like those two parents, they're divorced, and one's in California, the other New York, and the child goes over for once a week over to the East Coast to visit. That uneven sharing is what we're dealing with a polar bond such as hydrogen fluoride, where a hydrogen atom that shares it evenly has these electrons circling around in a fairly even pattern. Okay. As you see, there's one electron over here, one over here, but there'll be two over here sometimes, two over here sometimes. But in essence, they spend most of their time evenly being shared between them. So this is just some drawings and some clear descriptions on what exactly is going on with polar and nonpolar bonds. Now this is an electronegativity periodic table, and it shows you that the most electronegative is fluorine, and it decreases as you go to the left, it decreases as you go down, and so anytime you go down on the periodic table, they decrease electronegativity. Anytime you go to the right of the periodic table, it goes up in electronegativity. You'll notice that the noble gases are not there. Now, do you really need to worry about the electronegativity and calculating it? No, I won't have you calculate it in class. You do have to understand, though, that when you're dealing with bonds that are very some that are very clearly highly electronegative, like fluorine and oxygen and nitrogen, they're going to form these hydrogen bonds. So it's important that you know that these three are very electronegative, are going to pull in a lot of electrons and hold them tightly, and in fact form what we call hydrogen bonds, which is a whole nother type of bonding in between molecules rather than between atoms. When we're looking at single hydrogen bonds, they look like this, and you can form double, and you can form triple. We've done it in the classroom, so hopefully you get that idea. Here's some more discussion on what nonpolar bonds are. On the test, what I'm going to expect you to know is if you see two elements that are the same bonded to themselves, like two hydrogens, two oxygens, two nitrogens, two chlorines, two fluorines, two iodides, two bromines, all of these are nonpolar bonds by definition because they're bonded to themselves. You're no, if there were there's just two. If there were two of you, if we cloned one of you and put them in front of you, you would be equally strong by definition, right? So that's what we're dealing with here. Now with polar covalent bonds, it's a little different because here, remember fluorine, if you remember from the last slide, the fluorine is very highly electronegative, as we mentioned in class again. You have this hydrogen atom, which is less electronegative. When they're bonded to each other, when they share, fluorine keeps the electron more often. And so it's become more negative. We have that partial negative charge that I discussed in previous videos and in class. And then you have a partial positive charge on the other end. And so this becomes, one side becomes more negative and the other side becomes more positive. Not quite a full charge. They haven't separated. It hasn't become an ionic charge yet. But they do separate enough that it becomes an issue when the molecules start to interact. Delta, so the delta, again, this is lowercase delta. Lowercase, it represents a bond, a polar bond. All right, so if we went and looked at these, and you guys can go ahead and take some practice at doing this, and looked at these bonds. Again, I will not have you do it on the test, but it's important that you get the idea, so go ahead and do it for this activity. Look at these atoms, compare the electronegativity by rewinding and looking at the chart. You could have used the charts online, the charts I gave you in class. But in any case, look at the charts, and of course you have it in your paperwork as well, and compare the electronegativities of each of these and decide which one's more electronegative and which one's less electronegative, and go ahead and add the delta. Which side is delta minus and which side is delta plus. Partial positive and partial negative. Lastly, and probably the least important for when we're dealing with living systems, is these metallic bonds. It does explain, though, easily why electrons can flow through a metal so easily, and that's because metals share these electrons in almost like in a communistic way. The electrons share all the electrons are shared within the grouping of atoms, rather than each pair of atoms sharing electrons. So we have nonpolar bonds where two atoms are sharing it evenly. We have a polar bond where one atom is sharing unevenly versus the other. We have an ionic bond where one atom is taking the electrons, the other is giving it, and there's a positive and negative attraction between the two. And then we have these metals that are all kind of associated with one another, and these electrons, they kind of circulate around through the metals all over the place in this, let's go ahead and use the word sea, S-E-A, a sea of electrons, these ions sit. And it's an interesting visualization that you have all these electrons flowing through this sea from one end of the metal to the other. And that's why metals are such good conductors. This you should be able to do pretty well. And as far as drawing Lewis dot structures, you've been doing it throughout the project. If you take a look at bonds in HF, are they going to be ionic, polar, covalent, nonpolar, or metallic? The easiest ones, of course, if you have bonds in copper, you know they're going to be metallic. So hopefully everybody knows copper is metallic, right? And in fluorine 2, you also, the easier one, I'm just going to go ahead and do the easy ones, is nonpolar covalent. You know that as well. How do I know that nonpolar covalent is? Because they're bonded to themselves, right? Fluorine is bonded to fluorine. That's an easy one. The rest of this hydrogen fluoride, copper and oxygen, magnesium and chloride. Well, I'm going to go ahead and do that one because it's easy too. So I'm going to go ahead and do the easy ones. Ionic magnesium chloride, we did in earlier. We know it's ionic. And nickel oxide and bromium, Br2, we know again is nonpolar because it's bonded to itself. The rest of these, you go ahead and compare the electronegativities using that chart that you saw earlier, and see if the number that we discussed, 1.7 and 0.4, right? 0.4 being the difference between nonpolar and polar, which is this area here. And of course, over here is ionic. If the difference between the two atoms is greater than 1.7, then they're ionic. If it's less than 1.7 but greater than 0.4, then it's polar, and if below 0.4, it's nonpolar. I believe you can do that pretty easy. Now here, again, drawing the Lewis diagrams, these molecules should be fairly straightforward for you. It might be a little difficult with some of these, so let me go ahead and do some more difficult ones. You always want to pick the atom that can make the most bonds in the center, right? And we know that, for instance, bromine can only make one bond, because bromine, if we did that chart like we did before in the previous page, I think it was 3 pages. Actually, I think it was the first page. Bromine, just list the atoms. Bromine can only has 7 electrons each, right? It needs one, can only make one bond. There's 2 of them. Hydrogen has 1, can only make one. All right, can only make one bond, and that's 2 hydrogens. And then we have carbon, which has 4. Right. So bromine can only make one bond. Hydrogen can only make one bond. You're going to put carbon in the center, obviously. And if you're going to have hydrogens only going to bind to one thing, if it's all going to be one molecule, this suggests it's all one molecule, right? Hydrogen has to be bonded to it. Hydrogen has to be bonded here. Bromine has to be bonded here. And bromine here. Now, if you take a look at it, hydrogen has all its electrons in this bond. It only needs 2. It's okay. This hydrogen has all its electrons in this bond. Only needs 2. It's fine. Carbon only needs 8. So 2, 4, 6, 8. All of carbon's electrons are in these bonds. But there's one tricky part of this molecule, and that's that bromine, on the other hand, has 2 in each of the bonds, but then has all the other electrons, because it now has a full outer shell. So that would be the Lewis dot structure of this methyl bromide. Now, if you go ahead and do some of the others, for instance, here you have sulfur, right? It's in it do the same thing here with B. Let's go to B and do sulfur. Sulfur is one of them, but sulfur has 6 electrons in the outer shell. Oxygen has 6. Chlorine can only make 2, or 1 each, because chlorine has 7, and there's 2 of them. Now things get a little tricky, because here you might have more than one Lewis dot structure that would work, and that's okay. As long as it works, as long as you follow the rules, there's a full octet, and you don't have one atom with too many electrons, you're fine. So it doesn't matter whether you put oxygen or sulfur in the center, but you could do this. You could take and bond oxygen and sulfur together, and then you can bond. Now sulfur can make 2 bonds, right? So go ahead and make another chlorine here and a chlorine here. Chlorine only wants to make 1 bond each. Everybody here has a bond to itself. You're dealing with one molecule, all right? Although the Cl2 suggests that there's 2 chlorines bonded to oxygen, that would be wrong, wouldn't it? Because then it wouldn't be one molecule. It can't be. So don't go by this, this little subscript right before the oxygen suggesting that those 2 are bonded to oxygen. That's not the case. You have to go by how do we make one whole molecule while keeping to the rules of a full octet. All right, so now we just have to draw our other electrons. Well, we know we had 14 plus 12, right? 14 plus 12. So electrons, where did I get that? I got that from here. 14 plus 12. So it's 26 electrons total. I have 2 here, I have 2 here, and 2 here. There's 20 done. There's 6 done, rather. I need 20 more. I need to place the other 20 electrons. Let me go ahead and get rid of those marks and say, well, I got to put 8 electrons over around each of these atoms. None of these are hydrogen. None of these are lithium. You know, I'm not dealing with hydrogen is the only one that could make a bond and have a full octet completed. So here's 2 for chlorine, 3, 4, 5, 6, 7, 8. There's 4 for sulfur, right? There's 2 here and 2 here. So 5, 6, 7, and 8. There's 2 for oxygen there. There's 2 for oxygen here. And there's another 2 for oxygen there. So it's 2, 4, 5, 6, 7, 8. And then 2 here. 3, 4, 5, 6, 7, 8. So let's count them and see if this works. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. There were 26 electrons. I placed all 26 of them. This atom has 8, 2, 4, 6, 8. This atom has 2, 4, 6, 8. Yes, I counted these twice. I counted these 2 for the sulfur and for the chlorine. That's the point of sharing. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8. It's one molecule. All 26 electrons are accounted for. Check, 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 check. We're ready to go. So you would do this with all of these atoms, and it's just covalent bonding, and it's just drawing Lewis dot structures. I'm sure you can hit it. It's good practice. Then you do the same thing with these. There's some rules for you to follow in case you were confused. And it explains to you what a single bond is, what is a double bond, what's a triple bond. In some cases, you have to do a triple bond or a double bond in order to make the Lewis dot structure work. All right. So remember, there's more. Sometimes there's more than one. Check with your study groups. You know, this is due tomorrow. I sent you all this help because I figured you worked hard enough already on it this weekend. Hopefully you got it. You know that you're going to have some of this on the test on Monday. Good luck.